Well, thank you very much, Morten. Yes, I should first emphasize this is really joint work with a bunch of other people. In particular, I should mention Troels Henriksen and Martin, Henrik, Anna, and Cosmin here. Cosmin is also he's associated with the University of Copenhagen, DEGO, and is assistant professor working on high performance computing, expert in GPU programming and optimizations. And Troels is a PhD student on his third year. In particular, this project is about combining different tools. So first of all, we have a front end that basically takes APL, a subset of APL, and translates that into an intermediate language, a typed intermediate language. And then from that, the idea is to we have tried various kind of backends to target GPUs from that point of view. And we have now integrated the backend or the framework here with something called the Futhark language, which is this language developed. It's a functional language for running on GPUs, and I'll say a little bit more about that. The goal, of course, here is to have to provide high performance at the fingertips of domain experts. And then why would we choose APL as a tool? Of course, everyone here knows why that is. That could be a good choice. Well, APL provides this powerful and concise notation for array operations, right? And also, programs are really inherently parallel. And not only are they parallel, they're really data parallel, many of them. And of course, it is possible to express more sequential dependencies, and that's of course important in many cases as well. But at its key core, we have these data parallel operators and functions. There's a lot of APL code around, some of which is looking to run faster, I guess. And the challenge here, and there are plenty of challenges, but first of all, the one thing we are tackling in the first part of the project here, in the APL to tail compilation here, is that APL is really dynamically typed. That's really the essence. But we need to do something else to generate efficient code. We kind of need some type inference at the very front to make sure that we really have information about ranks, information about the data that's stored in these arrays, and so on. These functions are really ranked polymorphic, and we want to have more control over when we generate code. For what instances of use of these operators are we talking about? Many of the built-in operations are, of course, overloaded, at least from the point of view of the syntactic view, and types are really value sensitive, meaning that you get these promotions from booleans into integers more or less automatically in APL. We have tried to say, well, what we want to do is to take kind of this subset of APL where we give the programmer some control and still have a kind of a feeling about that, well, we need to deal with, we need to be able to statically determine the type of the data stored in these arrays and the ranks of the arrays. But remember, we are talking about a whole program optimization and compilation technique here. So it doesn't mean that for every single operation in your source program, you can definitely have ranked polymorphic code. It can be used many places, but each instance of those uses needs to you need to be able to statically determine the ranks and the types of the elements. So that problem has been tackled somewhat, and I'll say a little bit more about that. Before I go into this, I'll just mention briefly, the setup here, what our focus has been, and also maybe a little bit about the limitations and some of the things we'll never probably dive into. The approach we have taken is to take the dynamic function syntax for functions and operators, including trains, and we have then a front end to deal with that, and that we can compile kind of whole programs into this intermediate tail language. We try to make all the operations compatible with Dyalog, so you could potentially run your examples on an interpreter, and then basically move the code into this other realm. The front end provides all the scalar extension, identity, item resolution, overloading resolution, and so on, and then it produces this intermediate language representation. For the limitations here, we are strictly talking about static scoping. We don't allow updates of functions dynamically and so on. And also we depend on the static rank inference. So you cannot have code that dynamically that basically changes the rank dynamically of some data structure. Then that needs to be statically determined. And we have a whole program compilation technique, and of course no execute. And there are probably quite a few other limitations here. Right now we don't support nested arrays, for instance. So tail as an intermediate language, this idea of having an intermediate language where we can basically say, well, we want to investigate this kind of thing in isolation from everything else, from backends, from front ends, and so on, and so that we can kind of have an understanding what are these operations and what are their types in this setting, and you can see here for each of them, once you have basically done some overloading, you can say, well, we assume that for instance, rotate has this kind of type. It takes an integer, and then it takes some array of some rank, and then it basically gives you back another array of the same rank. So that's basically the type here of the rotate. So trying to understand the operations as being typed, and of course that only works if you can do some overloading resolution, because as you all guess, rotate also can have a more specific type where it says for an individual vector, it actually knows that the result that it gives back has the same length as the argument. So we do support these kind of things as well in the type system. And there's a whole theory about that, and there's a dynamic semantics, and you can prove that these are kind of related. And so the idea here was to kind of investigate in isolation this language. That has actually turned out to be quite helpful, and also allows us to investigate various paths. We have tried different backends from this tail language. One is just a simple C backend. Another one is to target the Haskell Accelerate library, and another one is now this Futhark backend language that we are targeting. So here's an example, just from the tails point of view. So here you see some APL code here, the mean and the variance and the standard deviation using some train symbolic Mongol jungle, and then it's going to translate this thing into this tail language. Of course, you're not supposed to write programs in this tail language, but it has kind of an explicitly typed annotation. And now we can really see what does this mean, and we have a theory of that structurally from the point of view of a programming language researcher or programming language technology expert who knows about how to compile such languages and so on. So that's basically the traditional approach. You build up an AST for your compiler here, and then you can take that and you can do. Here's an example of doing interpretation on that thing. You will get this value, but you could also go and compile it to something else, and then interpret that result or run it on a machine or whatever. So that's a basic a basic example here. Then the tail language is expressive enough to capture some of the, and that was quite important for us to not have to deal with all kind of multi-dimensional array operations, and we would like to take some of that and then compile it into something more specialized. So here's an example where we use the Guibas and Wyatt encoding of the dot operator, so now I've just written it up here as an operator dot, right? So you can see here the use of that. So it's used for with the inner product here with the plus and multiplication, and then two arrays A and B. And what will happen is actually that this code will translate into some tail program, and then a lot of simplifications will happen, and you will then end up with this tail program over here. And the point being that we can actually do simplifications on these objects. And then after that, we can then evaluate and interpret them, or we can compile them into to other things. So that's an example of saying, well, the language is expressive enough to capture these more advanced operators that basically work on all ranks, and still get some code that is for the particular use here, where it's matrices. There we then know that it will compile into this thing. But if we applied it to something of rank 3 here instead for A and B, then it will also compile into something, but something different. So something about the Futhark compiler. It's a pure, eager functional language with second-order parallel array constructs. And that means that we have these, we call them SOACs, second-order array combinators. That means that we have reductions, scans, all these kind of operations that take functions as arguments, first-order functions as argument, and then can work in parallel on those, and then of course data, and then work in parallel on those things. It does support also imperative-like constructs. And those are, of course, important, as we shall see later, for iterative computations, graph shortest paths, and so on. And what this is actually that it's a sequentializing compiler, not a parallelizing compiler, right? So there's a lot of parallelism available in these APL programs. I think Bob Benecke quoted that once. What are we going to do about all this parallelism? And that's basically the task of this Futhark compiler, is to figure out when it's important that we sequentialize, and when it's not important that when it's important that we keep things parallel, because there's a lot of parallelism available in the source code. So we call this a sequentializing compiler. And really, what we obtain here is something that is close in performance, close to the performance that we can get with something written in OpenCL directly. It of course performs various optimizations, constant folding, for instance. When you have some take operation in APL, you take some number of elements from some array. Either it could be of any rank, or number of rows or whatever. Then, if we can statically make sure that n is really less than or equal to the number of elements in the first dimension here, then we can skip this branch, right? We can eliminate the check. So there's a lot of constant folding happening inside the compiler to optimize away paths that are not going to be executed at runtime. Loop fusion is very, very important for these GPU programs to run efficiently. You need to do map fusion, for instance, map fusion. You need to do various kind of when you map over the result of a reduction, when you reduce over maps and so on. You need to be able to fuse these things properly. Otherwise, you would end up generating a lot of temporary arrays. And in particular, when people are talking about bit vectors and such, it turns out that in our programs we actually almost or very seldomly have to store these objects in memory. Rather, it will become control flow instead, whether it's or at the real data level. data parallel level, whether you execute one code or the other. So only in some cases, of course, you will need to have the bit vectors represented, but very often you can do without. Simply the Fusion will take care of not implementing or storing intermediate results here. Then, of course, we need to kind of flatten if there's a reduction inside an each or something like that. Then the big question is, when should we parallelize? And it needs to have some way of utilizing all the threads on the GPU and so on. So there's a need for some kind of flattening and so on. Also of big importance is this dealing with low-level GPU optimizations like coalesced memory accesses. So that's going to be quite important to get something of great speed. Okay, so here's an example just from compiling all the way. So this is just doing a simple integral in APL, compiling first into tail. This looks like this when it's pretty printed a little bit. And then we can translate that into Futhark. And one can say, well, it's not really that much of a difference here. There's somewhat a difference in the way you map over things. I won't come into that here, but basically you can see that for this case at least, it's quite straightforward for the compiler here to translate that into Futhark. But still, we were able to have these projects as totally separate projects. And that has helped us a lot in basically developing this in parallel, so to speak. So this was one example from just showing the full path of the compilation step here, and then of course the Futhark compiler will take care of compiling this into OpenCL code. And then I want to show some performance compute, some benchmarks here, and here we see some examples of compute-bound executions. We have, for instance, a signal analysis functionality here. There's this integral thing, and there's a Black-Scholes and another benchmark here. And what we see is that for this kind of code, we can basically get a lot of speed up compared to handwritten C code. So this is handwritten C code, and if you're interested, you can go online. We have all the benchmarks here. You can also investigate the C programs themselves and see what are they really doing. Are we cheating here or something? But they are actually quite optimized by the programmer, trying to do as little allocation as necessary and so on, and fusing things when necessary. So we are not just storing things and mallocing a lot of things. So it's really done the way the C programmer would do it. Also for this the integral example here. And even in this case for the integral, we get a lot of speed up since we can simply use all the threads on the GPUs here. So that shows out pretty nice. Then for other examples, it's not as nice, and I should apologize here that you don't see the one-liner live example here, but because we don't have the nested arrays, so that means that we will need to do something a little bit differently, and also we would like to avoid some kind of concatenation here. So the way we did it here was to basically, this is going to be rotating this is going to be working on rows, right? And so it's going to slide the game of life boards, and then that's used here 3 times to do to up and down the board, and then you do this check here with the neighbors. So that's basically the game of life here, and in this case, then we're just doing 100 iterations of a board, which is, I think, 900 times 900, I think, in this case, and then based on that, we will then see that we get a speed up, but it's not as big as before, because now we are doing these stencils, and they are not that you know, there's some overhead in the way we do that, and probably we can come back to investigate that a little bit further, how to do it. There's still some improvement of writing it up in C. So then I want to speak a little bit about whether, from the point of view of a programmer, sometimes you see problems that you need to, you basically have different algorithms for solving a problem. And there's a big, one can look at whether that should be an algorithmic choice or whether that should be a compiler choice, right? But here we take the approach that sometimes the programmer probably have some intentions, and for instance, one example is if you look at the Mandelbrot example, if you recall, it's something you have the complex plane, and then you're going to see whether some equation is going to be within some limit after you execute that a number of times for each of the images, and if it falls into the set, then it's part of the Mandelbrot set, and otherwise it's going to be escaping the Mandelbrot set. And then you're counting the number of iterations necessary to prove that it falls into the set. And so there are different approaches to solving this task. One is to say, well, we want to sequentialize at the very and this depth is kind of the maximum number of depths you want to dive into. So you take basically the complex plane and then you sequentially operate on one image at a time. And then inside that you want to say, well, for each pixel, and now you're dealing with each pixel in parallel, you want to just say apply this one function, update the on the image, and then you want to store that back into the object, and then you continue again with the next sequential thing. So that's going to be quite memory bound, and if you implement that with our setting, and we have done so, then you get something that basically flattens out a little bit here with the width and height of 1000 here. You would get a speed up over the C implementation of about 11 or something like that. Now another approach could be to say, well, I actually want to do something differently. I want to work on each point in parallel, but then inside here I want to have a sequential loop running on each thread, which is going to execute on each thread sequentially, and then counting the number of times that is necessary for the depths, and updating back the point here. So with that algorithm, you get something much better. So now you can get a 350 times speed up compared to the C equivalent of the same thing here. That turns out that is then compute bound instead, right? And we're basically running on and utilizing all of the threads, and that turns out to be quite important, of course, as you can see here. And this is the Mandelbrot examples, just for you can see here. We even got on another kind of benchmark computer here 672 times speed up compared to this. Okay, so I'm going to show you a few demos here for the last 5 minutes of the talk here. So some interoperability demos that we can actually run these things in practice. And the first demo is a demo of the Mandelbrot set. So the way it works is that we can generate from an APL program, we can basically generate a Python module that is, and then we have some glue code for actually dealing with the graphic cards and loading data in, and so on. And then we pass that data to, for instance, of course, in this case, there's not much data to pass in. It's just the coordinates and so on. So we pass that to the graphic card. It will compute on it and give you back an image that this Pygame thing can then display on the screen. And then a few milliseconds after, it will do the same thing again, and it will interact with the user using the mouse or using the arrow keys on the keyboard here to navigate and zoom in on the Mandelbrot set and so on. So let me show that in action here. So first we are going to select the which one, and I actually think this the screen is using the. So we're just using one of the GPUs here. So now you can play around and you can zoom in on the set here. And this is really the APL code running, generating these things, right? So then there are different ways to do nice features here with calculating the maximum steps, changing the maximum steps before you go out of this stuff. So this kind of interactive program, of course, we would like that to be able. We would like that to be possible from within Dyalog APL, of course. And I don't think that's a lot of engineering work, of course, to make that happen. But we have talked a little bit to people about being able to take a kind of a namespace, get all the code for the things, for the functions in there, and then be able to compile that, and then be able to to spawn into these things and show things. So the Pygame in Interpreter, what we would also like to do is to have something that runs on a 4K display efficiently, right? So right now we're basically copying things from the graphic cards onto the CPU, then we're copying it back to display it, right? And of course with OpenGL or something like that, we should be able to basically just show immediately the data and have something run in much higher dimensions and so on. So that was one of the examples. Let me just close that here. And there's 1 minute left, and I want to just quickly. Here's the live example. That was not live. It was alive. What? Did I copy the wrong one? I guess. So here we have live on a big board running. So, and it has some possibility you can do something. I think you can stop it. Put some gliders in there or something, and then you can run and so on. Yeah. So of course the last one I want to quickly show you is also to do various kind of stencil operations on the webcam. Why is it doing that? Because I'm using there we go, the APL cam. Yeah, sorry.
We can see the last one.
There it was. So you will have to work. This is me. There's some you can do some inversion things. These are having basic some filters running in APL code running, and then you have a stack of those being operated on and so on. Yeah. All right. So thanks.